Okay, guys, so we're on to creating geometric figures where we ended up yesterday. We talked about a straight edge. This straight edge is a ruler with no numbers, right? And a compass we talked about, which is a tool where you use a needle. Usually with these kinds of compasses, use a needle, but it can be any tool where you set and fix a center point, and then you use this part up here to set and fix a distance between the center point and all of the other points, right? And then that can be used by twisting it around to establish all of the points that are the same distance. So really think of the compass as a way to establish a fixed distance. And obviously a protractor is a tool that measure angles. Okay, it's used to measure angles. And, if we're using a ruler, these would be marked on the straight edge, the length, and you can measure length with a ruler. So that's why they call it ruler and protractor. Those are measuring tools. Whereas a compass and a straight edge, these are just tools where we're not using measurements, but we are using specifically what we call construction tools. So these definitions are kind of important right now. Okay, when you sketch a figure, that's when you just draw it the best that you can. You don't use any tools at all. When you draw a figure, then you're allowed to use the measuring tools, okay? Drawing is more accurate than a sketch, and you're going to use tools like, okay, I'm going to make sure this side is, 6 inches long, so I get my ruler out, right? And I measure the length here, right, using the ruler. Or I measure the angle to make sure I get the right angle that I'm looking for here. And generally speaking, a sketch is not usually very good, but a drawing is usually pretty good. It's a lot more accurate than a sketch. After that, we have constructions. When we do constructions, we're only using a compass and a straight edge, okay? So they want us to sketch and then draw each figure, okay? So we're going to try and do that here. What we have to do is we have to use tools to, well, we just don't have to use tools to sketch. Sorry, we can just sketch. I can just kind of draw here. Let's see. A square. I know a square is supposed to have sides that are the same length, and I know it's supposed to have all right angles. So I'm doing my best. I'm using a mouse here. Oh, it's not very good, is it? All right, but I'm going to try to make this be approximately, the best I can do. If this were straight and that were straight, well, I'd have a better chance. This corner looks like my best one here, right? That might be a right angle. But assuming that, I had a right angle here, oh, that's horrible stuff, right? Okay, so these marks right here, the little squares right here in the corner, tell me these are right angles. And then we use a single mark across the side. And this single mark means that the side length has been measured, right? And if we put a single mark on each side, then that means that measurement is the same. So here we have a shape that has all four sides supposedly measured and the same. This is just a sketch though, right? So this isn't actually, very accurate, right? Okay, let's see if I can get, I take that off for a second. Let me take that off. Okay. So now here I am on a site we call GeoGebra, and I should be able to construct a segment of a given length, right? So that's a segment of a given length. So when I draw a segment of a given length, that means, I can say, well, I want it to be exactly 4, right? So now I can also use, let's see, an angle with a given size. So I would kind of go like this and say I want this to be a 90-degree angle and say OK. And so now it's going down here, and then I would, let's see, I would connect those guys right here. So let me get my drawing my segment tool out here so that this and this is connected, right? And then I go back to my angle tool where I'm going to measure this angle from here to here and do 90 again, right? And then I should be able to draw the rest of this out using this tool here. Okay, so just like you would measure first using the ruler, how many inches across you want to be, and then you would use the protractor to measure 90 degrees, right? And then from that, you go measure the length, and it would be the same distance here. And then you would do another 90 degree and go the same distance. And then these are going to have to be 90 degrees as well. And we will confirm that by measuring the angles here. Let's see if I can measure this angle. Should also be 90, which it is. And then this angle is also 90. Right? And there's those marks that show that these are right angles, right? So these two sides are perpendicular to each other. And now I'm going to measure the length. This measures the length, so I should be able to click on the side. Oh, wow, 4 exactly. Oh, that's pretty good. I don't know how that happened. Might be rounding a little. But you can see whatever it is, those 4 are all exactly the same length. So this is how you would do it. You know, you'd use your ruler, and again, you'd use your compass. I want to kind of go over that compass again real quick with you. Looking at this tool here, or the protractor rather. So the way that you make sure that you use this protractor, I'm going to see if I can zoom in on this a little bit more. Okay, and drag that kind of up in front. So just to make sure you know how to use this. So once you have this side drawn out, I'll go with a different color here real quick. Get something that's going to stand out. So I would have, when I have one side, you know, drawn out with my straight edge, then I would have that drawn over here. I would go to the corner here, I would go look straight up at the 90, and at the end up here I would make a little teeny mark on my paper, right? And then I would use that mark, and this has got to line up right in the hole in the protractor, right? There should be a hole right here where you can line it up and make sure that this end of this segment is right on the hole. Come up here where the 90 is, and then you can lightly sketch, right? You would kind of draw a lightly sketched line, and that would tell you that you were, oh man, I'm terrible at this. That would tell you that you're coming down here at a 90-degree angle, right? Okay, and then what you do is you measure, because it's a drawing, so you're allowed to measure whatever length this is. You would measure the same length up here, and then you would make a mark, and then you would go back with your eraser. I don't know if I can do this. Let's just see if I can. This won't exactly be an erase. I'm going to erase this whole thing, right? And then I would go down here and I would erase. So now I'd have a 90-degree angle. And I just take my protractor and rotate it and do this again. That's how I do it, okay? So that's kind of the idea. Take that off, okay? That's kind of the idea there for how you could get that drawn, okay, compared to how you would just sketch it. So an isosceles triangle, so how would I do an isosceles triangle? An isosceles, this word isosceles, what it means is it means two of the legs of the triangle, two sides of the triangle are exactly the same length. So again, it wants me to sketch it, so I'm going to sketch it by just, oops, let me erase that. Let me get a different color here, sorry. And I'll go with this dark blue this time. I think I have actually, there's a straight line, so hopefully this will work for me, right? So I'm going to draw a straight line like that. And then I would measure this with my ruler. And then I would just come back over here and I would draw a straight line measured with my ruler to be exactly the same distance. And then this side doesn't matter how long it is, I just connect it, right? And then when I finish that, I would mark that this one is congruent to that one. And that's how I would end up with a drawn isosceles triangle, because I'm measuring it all, right? But if I was just sketching it, then I would, you know, not even using a ruler at this point, right? Or any kind of tool. I'm just freehand sketching it. And I'd say, okay, those are isosceles. And I mark them that they have been measured and that they are congruent. Okay. Go ahead and get those done. Okay. Now, we want to draw and label 3 coplanar lines. And we've talked about skew lines a little bit yesterday. So here we go. They want us to draw and label 3 coplanar lines. So to start with, what I'm going to do is I'm going to draw, I think I can make a box here, right? So I'm going to draw a box that represents a plane, right? And then inside of the plane, I'll pick another color here. I go with this purple color here, maybe. And since it says to draw it, I'm going to go ahead and draw it like this. Oops. And I need to put another arrow over here, which I'll do in a moment. And pick another color for my second line. Let's go with this guy. All right, there's another line that's coplanar. And then a third line. Right here's a third line. And then all I need to do is just add the arrows on the other side, right? That would be drawn, and then I'd need to label them. So how am I going to label them? Well, remember that you can label these lines, right? You can label them by just simply, finding points. You can establish points on them and then name it by the points. So I'll do one that way. But otherwise, the more simple way to do that is to simply do it like this and use a lowercase italics letter. So I might call this lowercase p. So that would be line P, and this might be line lowercase q, right? And this could be line lowercase r, right? Okay. Otherwise, I could pick 2 points on a line, like this one here and this one here. And with capital letters, maybe I call that A, and I call that B. And then I would say, okay, I have, let's see, line Q, line P, line R, or I can just use the symbols, the notation for a line, putting down 2 letters and put the symbol of a line over it. This is the symbol, right? It has to have arrows on both sides to show that that line goes forever. So I have drawn and labeled 3 coplanar lines. And this would be in a plane, and maybe I'll call this plane Z, right? This is plane Z. Notice they're all on the same surface, so they are coplanar, and that's what it means to be coplanar. Right? Coplanar lines, all in the same surface. All right, here we go. Let's try the next one. Describe the location of 2 skew lines. Okay, so the location. So I need to explain where I see 2 skew lines. So one line might be where the ceiling meets the back wall where the exit door is. And another line might, be where the 2 walls meet by the computer at the front of the class. Okay, and that would be the wall that goes straight up behind my computer, where my computer is. And that wall, so maybe I can, let's see if I can do a little sketch here. All right, so I have this is our classroom, right? I have the ceiling up here. I have the wall over there. So here's our drinking fountain, right? Drinking fountain's over here. And then this wall comes down here where our back door is, over here somewhere, right? So, and then this is the floor, and it runs back towards the back wall, right? Or towards the door. And so I have this wall right here, right? That is one, and then one line, and then I have this line right here. So this would be the front of my class over here where the projector is, right? The screen up here on the whiteboard this is my desk over here, right? Where the computer is or whatever. And this line right here represents another line. The 2 of them are skew. They will never touch, and that's because they are not coplanar. They do not exist on the same plane. Okay? Right, let's keep moving here. All right, so it says use undefined terms to define new terms. All right, so here we go. So array. Array is a part of a line that begins with a single point and extends infinitely in one direction. So the end point of array is the single point where the array begins. So array is named using two capital letters. The first representing the end point and the second representing any other point on the array. So we've got a new object, right? We've got a couple new objects. We have an endpoint of array, and we have the array itself. Okay, so the property of array, so it is a set of points, right, that starts at a single point and moves in one direction forever. So what are some properties of it? Well, it has a location, right, and it has a direction, right, but it doesn't have a length because it goes forever, so it can't be measured, right? So it says sketch and label a ray AB. Now it says ray AB, so I'm going to have to use, let's see if I can let me get a different color again. Let's go with this guy right here. So it would go from A through B and have an arrow to show that it keeps going, and that would be ray AB. Now it says sketch and label ray BA. So using these same points, A and B again, you know, I know that because the B is listed first, now it's a different ray. Okay, they may have some part in common, right? But they are not the same ray. This one starts at A and goes that direction through B. This one starts at B and goes this direction through A. And so when it asks me this question down here, it says, are ray AB and ray BA names for the same ray? The answer is no. And the reason not, they do not have all the same properties. In other words, they have a property of location. So where's the location of AB? Well, it starts at A, and it's all these points to the right of A, towards B, and beyond, including these points over here. And that is not part of the properties for ray BA. Ray BA does not include these points to the right of BA. It just includes this common part and then an uncommon part to the left, okay? So they are not the same rays, okay? And that is why. You want to explain that? And maybe I'll scroll down here and type in an answer real quick. All right, you can follow along and put your own answer in here. The rays are not the same because they don't have the exact same properties. They do not contain the same points because one starts at A and goes to the right through B, while the other starts at B and goes to the left, through A. So they're not the same. Okay, now they want us to get some practice in here, naming geometric figures. So they want us to use symbols only to name this figure. So we see that this is a figure that has an initial point, right? An initial point, which actually, was it that what they called it? They call it an, oh, sorry, let me grab this here and see if oh my gosh. Let me take that tool off and go back to, let me get that guy out of there and then go back to grabbing, oh man, I'm not able to grab it. Okay, so they're calling this the end point of array. A lot of people call it an initial point of array, but anyway, we're going to use the symbol. So the initial point or the end point of the array is G. So I'm going to, let's see, draw this out. What the name is using the notation, starts at G, goes through F. It is array, so it gets a line over it like this, and an arrow going above, but to the only over F. No arrow on this side. If you put an arrow on this side, then it would mean the line GF, right? And this is not the line GF. This is the ray GF. Starts at G, goes through F. Okay. All right, now we have a line segment. A line segment is another object. It's a different object, right? So a line segment is all of the points between 2 points, right? So start with 1 point and go all the way over to the other point and include every point in between them. And that then makes these 2 points where it begins and ends, they're called endpoints, right? Those are the endpoints. And for a segment, we use the symbol, with the 2 letters that represent the A and the B, okay? And then we put the bar over it, but no arrow because it doesn't continue. It stops. So here we go. It says draw and label that. So to draw it, I'm supposed to draw this, not sketch it, huh? So that means I can use a straight edge. Well, I'm going to use this tool to make sure that it's straight. AB. And now segment BA, which is that segment. And now, are they both names for the same segment? And the answer is yes, because they are all the points that start at A and go through to B, including A and B, but not beyond. It doesn't matter which direction I go in it. They have all the same properties. They have all the same points that make this up, right? So if they're all the same points and all of the properties are identical, then it's the same object. It's exactly the same object. And so we would say, yeah, this segment and that segment are just 2 different names for really what is the same line segment. So let's put that in there. Oops, I gotta turn that off and come over here. So they are the same line segment because they have the same set of points. Their properties, which in this case is location, and location and length. Location, what else do we have besides location? We have location, direction, and length are identical. Because of that, the objects are exactly the same. So these segments are the same, even though we use the same name for each object. Oops, even though we use different names, sorry. Different names for the one object. For the one object, we have one object, which is a segment. We're using different names for it, but honestly, it's the same object, isn't it? Okay. Now it says use a ruler to measure it. I'll let you guys go ahead and do that. Go ahead and measure that. And I don't think I have a ruler tool here to measure this. So I'm just going to make up some number. You're going to have to put in the actual number here, right? So AB is equal to 4 inches. Now, notice the notation here. This is really kind of important. That notation there, it says AB, but notice that it does not have any mark over it. And when we don't put the segment mark over it, that means we are not talking about the object of the segment. So here's what it looks like when we're talking about the object of the segment right here. Down here, we don't have that segment over it. So we're not talking about the object. We're talking about the properties of the object. That's why when you read this, I know that's just like such a silly thing. In fact, let me draw this out just to remember. Yesterday, remember we made this table. It's on the, it's on the back wall, right? We said there are objects, right? And then there are properties, right? So in this case, right? The object that we're going to use, let's see if I can do a text area here. So right here, this would be the object side. And this would be the, what's going on with that? This would be the property side, right? So the object is the segment. Oh, man. And then over here, the property is the length. Okay, so it's not all staying on the screen for whatever reason, but that's okay. The length. So we have the object is the segment and the property is the length, and you're getting that. So when I use this mark right here, right, then that means I am talking about the object, right, which is the segment itself. When I take away that mark, that means I'm not talking about the object anymore. It means now what I'm talking about is I'm talking about the property of the object, which is the length. So it says AB equals 4 inches. And this is read as the distance from point A to point B. Again, we're talking here, this is the key word, we're talking here about distance. We're not talking about, this is not talking about the segment. This has nothing to do with the segment. It has everything to do with the distance between the points. Okay? Now over here, the measure of that segment, this is the property of the segment, right? It is saying AB, but that little m in front of it means the measure of segment AB. The measure of segment AB. So guess what? Well, what that means is that I'm going to be talking about its property, and that property is the measure of it, and so that's going to be 4 inches. So I'm not sure why I'm having trouble here with the text tool. There we go, and it should say 4 inches there, and so the measure of the segment is 4 inches, right? And this one right here, the distance between them was also 4 inches, or whatever you measured it out to be. So how would we read this? Is this talking about the segment? Is it talking about the distance between 2 points? Or is it talking about the property of the segment, which is the property of its measure or length, right? So in this case, because that little m and the segment mark, it is talking about, this is saying the measure of segment CF is 3 inches. So there we are again. Here we are talking about the property of length when we use this notation. So why do we go through all this trouble? I mean, you might be sitting there going, oh my gosh, Mr. T, this is just so stupid and boring. But it's because later on, a lot of times, we're going to be talking and doing proofs and talking about these objects, and we're going to get very, very specific. And we're going to be using sometimes this notation when we're talking about the object, sometimes this notation when we're talking about just the distance between 2 points, and sometimes this notation when we're talking about the length of an object, right? Or the measure of the object, right? Anytime we've measured an object, in this case measuring the segment, okay? All right, and then let's go down here. It says, how would you read SP equals 8 inches? Okay, so that is not talking about the segment. So we're talking about just the distance between the points. So we would say the distance between points S and P is 8 inches, right? And I think they wrote it up here. The distance from point A to point B, so we could say it that way too. It's another way to say it. The distance from point S to point P is 8 inches. So that's just another way. It seems like it's talking about the same thing, but the reality is it's not quite talking about the same thing, is it? Okay. So now we got to use symbols to name these things. So what do we have here in this first one? Let's draw some of these guys out. So the first one is, does it begin and end? Yes, then it's a segment. So this one is, oops. Oh, I don't want to use the text tool. Let me get back this freehand tool. And so this would be, we're going to use F and G to identify it. and then it's a segment, so we put the line over it, but we do not put the arrows, right? This is line FG. So we use the F and the G. Oops. And then we put the line over it, and because we put that bar over it, because it continues forever, we're going to put the arrows over it, and now we know we're talking about the line FG. Then down here we have ray FG, so we would do the F and the G, and my computer's having a hard time keeping up. So ray FG, okay? And that's the difference. Segment FG, line FG, ray FG. It's expected that you know these, okay? For sure, that you know what we're doing here. Okay. It says if two line segments have equal measure, then the line segments have the same length. Congruent line segments are two or more line segments of equal measure. So this is we get into something, a new word called congruent. Something that we talk about things being congruent. And when we talk about objects, right? In geometry, we're talking about objects. You hear me keep talking about this. And we're talking about objects that have all the same properties, then they would be equal, right? They would be exactly the same if they were exactly the same in every way. But when we're looking at two objects, like in this case, we're looking at A, B, and DC here. These two objects have been measured, and they have two little marks on them that match. So there's two here and two here. That tells me they have the same measure on them. That means that these two segments have the same length. But remember when we talk about a segment and then we talk about its properties of length, the property of length is the same, right? But what's different is the property of location. So because the location is different, I can't say that they're equal. I would never say, try to write this out. It would be wrong if I said AB, right? Segment AB. If I wrote this, segment AB is equal to, come on computer, there we go, segment DC. So if you put this on your paper, guess what we would do? We would, if you wrote that, segment AB is equal to segment DC, we would mark that wrong. We would say, no, they're not equal. They're not equal because they have properties of location that are different, right? So the only way something can be equal, two objects can be equal, is they have to be the same object. As soon as you move one of them, their properties may not be the same, and as soon as their properties are different, well, then they're not equal. That's when we use the other term we use. So let me just grab a color here, and that's when we say, okay, well, they're very close to the same, right? Basically, all their properties are the same except location. So whenever that's the case, then we would write out, use our notation to make these two shapes, or these two objects. So we're talking about segment DC, segment AB, and then we'd say, okay, here's equal. This means equal, but guess what? They're not equal, but they're close. So we're going to put this little thing they call the tilde on top. And this is the symbol for congruent. If you look right here, you'll see it, right? On your paper. Equals with a little squiggly on top, right? And then we're saying, there it is again, then we're saying the objects are congruent. And you read that as line segment AB is congruent to line segment CD. And it says the congruent symbol between references to congruent geometric figures. The equal symbol we use between references to equal lengths or distances. So if we're talking about measures or other properties, properties can be equal. Objects, if they're different objects, can't be equal. They can only be congruent, right? If they're different objects, they can't be equal. Otherwise, it would be the same object. Got it? Okay. That's a small little thing as well, but if you understand that concept, it's going to help you a lot in geometry. We get so many other problems like this. That thing's still there. What's that thing doing there, man? I haven't been able to see if I can ditch that somewhere. Probably not. Okay. All right, so it says draw and label two congruent line segments. Use symbols to write a statement that describes their relationships. All right, so we're going to do that. So I'm going to use because it says draw, I can use a ruler and make a straight line, and then I would use my ruler. Because this is drawing, we're allowed to measure and make sure they're the same, right? And then I'm gonna need some points here. So I would call this one, point A. Actually, I can do to make this look a little bit bigger. I can go here and put an end point there and an end point here. And an end point here and an end point here, right? And then go back and get some letters. So if this was point A and this is point B and point C and point D, and if I had measured them, and it says draw and label, so since I measured them before with my ruler, I would mark that I've measured them, and I would give them the same number of these little tick marks here to show, okay, they're measured and marked the same. Now it's drawn and labeled, right? So now I'm supposed to use symbols to write a statement that describes the relationship. So what do we know about these two segments? I have segment A, B, and segment C, D, and now I need to use symbol to describe the relationship. So how are they related? Are they equal? No, they're not. Remember what I said? We crossed that out because we said they can't be equal because they have different property of location. So instead we call them congruent. They're not equal, they are congruent. Okay? Ms. Snyder drew the triangle shown and asked her students to classify it. Maria says the triangle is an equilateral triangle. Is she correct? Well, what does equilateral mean? So if there's some of you that speak Spanish, you have a little advantage whenever we get in here using some of this language that has a Latin root, and Spanish is one of those Latin languages, so a lot of these words have roots that Spanish speakers can easily understand. So equal, so that's just like in Spanish or in English equal, in Spanish igual, right? And a lateral, so lateral in English, it means the side, right? And in Spanish, lado. So a triangle, de igual lado, right? Which means what that's basically saying, equilateral, it's saying that the three sides of the triangle are all equal to each other. 1, 2, 3. That means that we would know that TR is congruent to RY is congruent to TY. So she drew this triangle. She asked us to classify it. Mariah says it's equilateral. Is she correct? Well, no, because we don't have any evidence that it's correct. But now she's marked it. And if she's marked it after she measured it, she drew it and she drew the markers for it. And now we would want to classify it. So can we now say, since they have the same marks here, can we say that this is an equilateral triangle? So the answer is yes, it's equilateral. But Mariah now says, oh wait, it's isosceles. And Justin says, no, it's equilateral. So who's correct? Well, isosceles, that would mean that two legs are congruent. And a lot of people, they just use that definition to say at least two legs are congruent. So do we have two legs that are congruent? Yeah. So is Mariah correct when she says it's an isosceles triangle? Yeah, she's not incorrect when she says that. Justin says it's equilateral, igualado, right? So all three sides, equilateral. And Justin is also correct. It is equilateral. So when it says who is correct, the only thing that really makes me say Justin is more correct is because it's asking us to classify. And whenever they ask us to classify an object, they don't want us just to give it a name that sure it's true. They want us to give it the most precise and correct name. And so, you know, I can call this a triangle. Okay, it's a triangle. But the most correct name would be equilateral, because that tells me the most information about it. It is the most specific, right? Equilateral. Isosceles only tells me part of the story. It's not as specific. So even though all equilateral triangles are also isosceles, you always want to go with the most specific one. Now, let me draw this out for you real quick, right? So if I had a Venn diagram, oh boy. So I had a Venn diagram, and I had all these special triangles in here that were all isosceles, right? Oh boy. I think I'm gonna try to use this speech bubble here, right? I don't know, we'll see if that works, right? But they're all, I'm gonna write isosceles in here. I don't know if I probably made a mistake here. Let's see if I can type in here. Okay, well, isosceles, right? So they're all isosceles as long as they have, you know, at least two sides, right? But inside of that world, there's the extra special ones. So let me go inside of here and get a different color. And I'll go with a different color in here. And so then they're inside, there is an extra special set. And that extra special set is called equilateral. So I have all the isosceles triangles here. I think I can try to get that. No, it's not working for me. I don't know. And my equilateral disappeared, but that's the idea. All equilaterals are also isosceles. All right? All the equilaterals are isosceles, but then there are others that are just isosceles. And so when it tells me to classify, again, we're asked to classify, they don't want me to take the biggest circle. They want me to tell them what's the smallest circle that this triangle would fit into when I classify it. Oh, well, the smallest would be the equilateral triangle. So I would best be calling this or classifying this as equilateral. Okay? So now she says, right? Oh boy, I got to move this guy here. Okay, I don't know if I can move this or not. All right, it's there. And we'll see what happens with it later on. All right, whatever. Miss Snyder also asked her students to write a statement that best describes the congruency of the line segments. So Mariah wrote TR is equal to RY is equal to YT. And what is she saying here? Well, she is saying the distance between the points T and R is equal to the distance between the points R and Y, which is equal to the distance between YT. Is that correct? The answer is yes, this is correct. The distances are all equal. Justin, on the other hand, he's not saying the distances. He's saying segment TR is congruent to segment RY, which is congruent to segment YT. So here, Justin is saying the segments are congruent. Here, she's saying the distances are equal. This is true. The distances are equal, and it is equilateral. This here is saying the segments are congruent to each other. The only reason, so they both said true things. When it says who's correct, the only reason I would go with Justin over Mariah is because she wants us to write a statement that best describes the congruency of the segments. So she's asking us to do something about the congruency of the segments, then I would write the one about congruency of the segments, right? This is equality of the distances. This is congruency of the segments. So this fits a little more with what Ms. Snyder asked us to do. So I'm sorry, Mariah, yet again. We are not on the same page with you right now. So sorry. Okay. I wonder if I go like this, whether or not I can get that guy moved now. Maybe I can do something like this, and then maybe that'll let me see if I can move this guy. All right, it says use symbols to write 3 valid conclusions based on the figure shown. How do you read each conclusion? Okay, so we're going to, no, I still can't, oh wait. I thought I took that tool off, but I guess I didn't. I guess I did. All right, anyway, it's kind of stuck there, right? But I'm going to have to draw on this thing, so here we go. I have to ignore these little bubbles that I've created and can't make them go away because I'm not a pro at this software here. All right, here we go. I see that segment FG has a length of 10 centimeters and segment HI has a length of 10 centimeters. So that tells me that their properties or lengths are the same, and that means I can say that the segment FG, right? Segment FG, and I draw a line over it like this. I can say that that is congruent to segment HI. And that's one statement I can make. That the two segments are congruent. I can also make a statement about their property of measure or length. So I would use the little m for segment FG. Ay. Thanks for your patience here, guys. Write that out. The measure of segment FG is equal to, all right, you should be able to keep up with this because I am moving so slow. It is equal to the measure of segment HI. All right. Okay. And then lastly, you have the distance between F and G. So this one is written right without the bar over it, because now I'm not talking about the segment. I'm only talking about the distance between the 2 points. I'm not even talking about the segment at all. The distance between these 2 points is equal to the distance between these 2 points, right? And I'm going to let you guys, if you have to pause the video, I hope not, but if you had to pause the video, this would be a good place. You'd pause it and you would make the acknowledgement here, right, that the distance between F and G is equal to the distance between H and I. So that would be what we're stating here. 3 different things. First, the segments themselves are congruent. Second, the measure of the segments, which is a property of the segments, is equal. Third, the distance between the 2 points are equal. The distances between these 2 points and the distance between these 2 points, so the distances here and here are equal. That's 3 different ways, and how would I read it? You would write that out. I'm not going to write it, but you should. Segment FG is congruent to segment HI, and then you would say the measure of segment FG is equal to the measure of segment HI, and then you would say the distance between points F and G is equal to the distance between points H and I. Okay, that's how you would do that. All right, so it says use symbols to name all lines, rays, or segments shown. Okay, so what do we have? We have a line HG. And I guess we'll write these out. Man, I just moved so slow with this, so sorry to make you just bear with me here, but at least, at the very least, you should be able to keep up in your book. So we're going to say, first thing we see here is line HG. And that is a line, right? And then I also have, that part did not want to go up. Okay. Then I also have segment HG, which is just starts at H and goes to G. So I've got segment Come on, baby. Here we go. H. These are different now. Segment HG. Then I have ray HG, right? So ray that starts at H and goes through G. So it gets the bar over it and an arrow only over the G part. And then I've got a ray that would be the ray that starts here at H and goes through G. And then I've got a ray that starts at G and goes through H. So I've got ray G, H. Now notice that I don't just write HG and then draw the arrow going the other direction. That's not how it works. The arrow always goes to the right for some reason, maybe because that's the direction that we read in, right, is left to right. In our language, we read left to right, in our written language. So we don't just draw our arrow backwards, and then that would be kind of awkward, like, right? Okay, so this is ray what? I have to skip the H, get over here to the G, and come back. We just move the letters, and now we say, okay, so it's ray GH would be, the ray that starts here and goes that direction forever, right? Okay, so I can't see, maybe I'm missing something. Let's see, we got a line, we got a segment, we got one ray, and we got another ray, and I think that's all that we have there. So it says, explain when is it appropriate to use the statement JK equals MN, and when is it appropriate to use the statement segment JK is congruent to segment MN. So I would use this statement when I'm talking about the distance between points J and K and the distance between points M and N. And I want to say that those distances, the value, whatever one we measure it, whatever that quantity is, that these two quantities are equal. These two distances are equal. Over here, I would use this statement when I'm talking about the objects themselves, the geometric objects themselves, which are segments. So when I want to say this segment is congruent to that segment, then I would use this. So one when I'm talking about distance between points, another one when I'm talking about the congruency of objects. Okay? All right, now we got to figure out which of these are valid and which are not. So you should pause the video here and see if you can do this one on your own. See if you can do these on your own. And then I'm going to come back, and after you pause it for a moment, I'll give you a moment, and then I'm going to give you the answer here. Okay, did you figure it out? So we have here a triangle. We've got two sides marked, right? So these two sides are equal. They're marked congruent. They're marked that the sides are congruent, rather. They're equal length, right? And so this would be an isosceles triangle. So now we have to see which statement is valid. So this says segment HO is equal to segment TO. So I hope you got this right. But that one is not valid. We would never say that two segments are equal if they're different. They're different. They're not different in length, but they are different in location. So they are not the same segment, so they are not equal. This one says that segment HO is congruent to segment TO. Aha, that's true. The segments are congruent. This one says that the distance between H and O is equal to the distance between T and O. That is correct. The distances are equal. This one says the distance between HO is congruent to the distance between TO. Well, that's not true. We don't use congruent when we're talking about numbers. Numbers are equal, right? And that's this HO, the distance between that's a number. That's a quantity or a number, right? So this quantity is the same as that quantity. So we would use equal. So that one's not right. This one says the measures of segment HO and segment TO. These measures are equal, and that is true. The measures are equal. Are the measures congruent? No, because measures are, again, quantities. They're numbers, right? They're not objects. We're talking about the property of measurement of those segments, and that property of measurement would be equal not congruent. The segments are congruent, but the measures are not. This one says the measure of the distance between HO and the measure of the distance between TO, that is not correct, because we would not take the measure of a distance. The distance itself is a number. Then we're not going to take the measure of it. All right, so this one's not correct because we never take the measure of a distance. All right, that's like the measure of a number. We already know that. And this here is also not correct because it's saying the measure of the distance between H and O. Again, we don't take the measure of a number, so we will cross that out. That is not correct. Okay? Hope you got those all right, and I hope you understand why. There is a little bit, I'm sure, on the test about this, but more importantly, that's something that we are going to be using, and those notations, we're going to be using those all the time. So it's really good that you have taken the time to get this all like really figured out well, and I think you're off to a good start. Okay? Good job.